The driver for this work was the fact that uh, going to planetary bodies, including Mars, is very challenging, and is whatever instrument that you have to send, there is always the issue of mass and power constraints. So that's what it started. This work was that we wanted to come up with a laser that would be compact, low mass, and low power. We need to know a whole lot about the Mars atmosphere in order to design the spacecraft that are going to land on Mars. There is quite a bit of variation in the Mars atmospheric density. So with the laser beam, we can measure the Mars atmospheric density, its variation with geographical locations and seasonal variation. We can measure the winds and profile the winds globally. We can measure the aerosol concentration, the CO2 ice clouds that are plenty on Mars. And all these measurements we can do with the laser beam. In fact, we might be able to do all of that with a single laser system orbiting the Mars. And these are all important for designing missions to Mars. Even for robotic missions, these parameters are important because now if we know about the Mars atmosphere, we can design a spacecraft that are a whole lot more efficient, use less fuel. Commercial aviation could be a good beneficiary of this technology because for a long time, for the past 20 years or so, we've been studying of using laser systems that can measure turbulences and winds. In fact, we have those systems that we apply them as experiments on NASA airplanes as research. But the lasers are big, power hungry. This provides an opportunity, another opportunity to reduce the size and efficiency of these systems and make it more viable for such applications. If we pump these lasers at the wavelengths closer to the operating wavelengths, we can get higher efficiencies. Norm showed that through experiments, through simulations in the past, but now there are actually pump sources that are available. And so we have that, and that's the key part. The other key part was to use a composite structure for the laser gain media, so we can utilize all the pump power and waste very little of it. So through these two features, these novel features, we were able to get high efficiencies out of these lasers and make them very compact size and low mass, very suited for planetary applications. When we started this, we set a goal for ourselves. We said we want to improve the laser efficiency by order of magnitude compared to what is available now. We may not ever get there, but that's a goal we set for ourselves. And we are essentially about 1/3 there in terms of the efficiency. And we haven't really even touched upon a lot of optimizations that we can do in the lab yet. So we are very optimistic that we may not get to a whole order of magnitude, but we can get close to it. And even a factor of 5 improvement in efficiency would have a major impact on the instrument design and the overall mass and power of the instrument.